Hello everyone, welcome to the course on electromagnetic theory and interference. In this session, let us find the location of voltage max Vmax and voltage minimum Vmin by using a Smith chart. Here a load of 100 plus J 150 ohm is connected to a 75 ohm lossless transmission line. We are supposed to find the reflection coefficient gamma, VSWR, load admittance, that is YL, input impedance at zero point 0.4 lambda from the load, the location of Vmax and Vmin with respect to the load if the length of the transmission line is 0.6 lambda, and the input impedance at the generator side. So these are the given tasks to find here. They have given majorly Z0, ZL is given, and the length of the transmission line is given. So based on this, we are supposed to find the input impedance, right? First, we have to normalize the load with respect to characteristic impedance. Doing that, we get the R circle value, that is 1.33. So 1.3 is available here. Okay, I am taking 1.33 approximately is 1.3. This is R circle, and X circle is 2. So here the 2 value is present. So intersection of these two is a point P where the normalized load impedance is present. Taking O as center of the circle and OP as radius, we have to draw a constant VSWR circle. This circle passes the real part of the axis at 4.8, that is lying above that 5, right, or below that 5 we can say. And to find the magnitude of reflection coefficient, I have drawn a straight line from the left hand side of this VSWR circle to the scale down, and it is found at 0.66. Okay, where to find the angle of reflection coefficient from the real part of this reflection coefficient axis, how much angle this load location is making. So we have to extend this line OP to Q here, and if you could see, it is exactly located at 40 degree, the reflection coefficient. And to the next step, to obtain the load admittance, we have to extend this PO line to POP dash, since admittance will be located just opposite to the load impedance. And at the point P dash, we have to find what R circle and X circle is passing there. Since it is lying below, it's a negative reactance. Here, if you could see, it is located in this particular point, that is 0.23. Above 24 it is there, right? 0.23 minus J, if you could see here, it is 0.35 because it is lying between 0.3 and 0.4. To find the actual load admittance, we have to denormalize by multiplying with the characteristic admittance, which is the reciprocal of characteristic impedance here. And the answer is written in millisiemens or millimos also we can. To find the input impedance Zn at zero point 0.4 lambda from the load, we have to find where this load is located. P is the point where normalized load impedance is located, right? So extending this straight line towards the outermost circle where the wavelength towards generator scale is given there, we could see it is located at 0.194 lambda. Load is available at this location. So from here we have to move 0.4 lambda towards the generator side. Okay, from the load we have to move towards the generator so as to find the input impedance. So we have to add a 0.4 lambda to this particular location of load, and we get 0.594 lambda. Since the complete Smith chart is 0.5 lambda, we are subtracting from this value 0.5 lambda, we are getting 0.094 lambda. So we have to move this particular distance clockwise and find the location R where the normalized input impedance is available. So if you are able to see, it is 0.094 lambda, extending this point connecting the center of the circle where this straight line intersects this VSWR circle, that is the location of R where the normalized input impedance is present. So seeing here, we can see the intersection is exactly available at 0.3. This is a 0.3, right? This is a 0.3 R circle and X circle is 0.63. Okay, here it will be lying here. 0.63 means this point, the intersection of these two we have to extend by using our pencil, and we have to find this. So to denormalize, we multiply with characteristic impedance and write the final answer in terms of ohms. The next question they have asked is to find the locations of Vmax and Vmin. If the, with respect to load, if the line is zero point 0.6 lambda, okay, previously it was 0.4 lambda. So now if the length of the transmission line is 0.6 lambda means we have to find what is the voltage max and minimum locations. So if you could see here, the load is available at 0.194. If we add a zero point 0.6 lambda to it, what happens? It will come 0.794 lambda. 0.794 lambda means what? We are rotating 0.5 lambda complete Smith chart one time and 0.294 lambda next. So if you could see here from this point, if you move one times, we are crossing the Vmax, Vmin one time, right? Vmax one time once crossed to reach this location, two times we crossed the Vmax. So we get two voltage maxima and only one minima, because from here if you rotate and come to this point, one time we crossed here, here also one time, but to reach this location 0.294 lambda, we crossed twice this location, voltage max location. Since the length of the transmission line is 0.4 lambda, so we are able to achieve two voltage maxima and only one voltage minimum. So to find the voltage maxima location, if you could see from the voltage maxima, how much distance the load is available, 0.25 0.25 lambda minus 0.194 lambda. This is the distance, right, from the load. And to find the second voltage maxima, we can see first, if I want to see again one more maxima, I have to move 0.5 lambda. So I have just add 0.5 lambda to the first voltage maxima that I got there. And to find the voltage minimum is available at 0.5 lambda, load is available at 0.194. So taking the difference between these two only, the location of Vmin. 0.5 minus 194 is 0.306. So the final task they have asked to find the input impedance when the length of the transmission line is 0.6 lambda they have asked. So already we have found this location, right? If we add 0.6 lambda to this particular load location, we get 0.794. Subtract 0.5 from that, we get 0.294. 0.294 is available here. So drawing a straight line, and between these 2 points from the center and the intersection of this straight line with this circle is G. That is the point where input impedance is available. Looking here, we could observe it is 1.8, R circle, X circle is 2.2. So it is written as negative sign. So denormalizing with, how to denormalize with respect to characteristic impedance and write the final answer in ohms. So far in this particular problem, they have given the load impedance, characteristic impedance, and at two different length of the transmission line, like 0.4 lambda and 0.6 lambda away from the load, we are asked to find the input impedance, and at 0.6 lambda away from the load, we are asked to find the locations of Vmax and Vmin, and also these parameters, reflection coefficient, standing wave ratio, load admittance, they ask us to find. Hope you understood how to find the various parameters of the transmission line based on the given data. Happy learning. We will meet